We talked a bit last time about the binomial distribution, so I'm going to start there with a little bit more practice. And then uniform distributions was another thing that you talked about. And then you ended by venturing into the normal distribution. All those things sound familiar-ish? Or someone sent me fake notes, which would be hilarious. So binomial distribution stuff. If we're talking about binomial distributions, you're again thinking of situations where only two things could happen. Technically, more than two things could happen, but what you're doing is you're evaluating the situation as either this happened or this happened. So like you could give a survey and the survey could have a bunch of different answers on it, but to make it a binomial distribution, you would be asking people, did they answer that they were Democrat or something else? Like there might have been other choices on there, but if you turned it into there were only two options, Democrat or something else, that would still be binomial. But if it was Democrat or Republican or independent, or you put all those other options out there, that wouldn't be binomial. But if you turned it into only two things could happen. So something fails or something succeeds, that's binomial. You flip a coin and you get heads or tails, that's binomial. You shoot a basketball and it either goes in the hoop or it doesn't go in the hoop. That would be binomial. So things that have two things that could happen could be binomial distributions for us. So one thing about binomial distributions is that when we go to set them up, it matters a lot how we write out our probability density function. Did you hear that word yet? She might have written PDF for things. She wrote you the PDF for the normal distribution and it had some crazy things in it. And then she said, we're not going to use it at all. So for the probability density functions, we have a different one for each of the different distributions. When it's the binomial distribution, that's the thing where we have the combination something, choose something, where we have the factorials in there and all that stuff. That's with the binomial distribution. So I'm going to read you this example, and then I'm going to talk about how you would set this problem up. We're not actually going to solve the problem, but we're going to write what you would do to solve the problem. It would be like Dr. Whitener style, because she doesn't necessarily have you actually do all the math, but she'll have you set up how to do the math. This says a company has a fleet of 50 trucks, each of which has a 10% chance of breaking down on any given day. What is the probability that on a given day, at least 5 trucks will break down? So here's the thing. Two things could happen. The truck could break down or it could not break down. And since it's only two things, breaking down or not breaking down, that's what's making this a binomial distribution here. So in this case, when we talked about probability of success and probability of a failure, in this case, a success is a really weird thing. It's the truck breaking down. We don't normally think of that as a success, but in this case, what we're talking about, a success would be that the truck broke down, and that percentage is 10%. And then it's saying, what's the probability that at least 5 trucks will break down? We have 50 trucks. So at least 5 trucks could mean exactly 5 trucks, or it could be 6 trucks, or it could be 7 trucks, or 8 trucks, or 9 trucks, all the way up to 50 trucks. When you do a binomial distribution problem like this, if I ask you what's the probability exactly 5 trucks breaks down, that's when you do the n choose x, and then you go ahead and set up the probability distribution thing, and I'll write that all out. But in this case, we would have to do that for 5 and 6 and 7 and 8 and 9, all the way up to 50. Or, to answer this question, the other thing we could do is calculate the probability of the complement happening, which would be fewer than 5 trucks breaking down. And so we would do 1 minus the complement instead, and that would be a much shorter calculation. So what I have written in words there's a lot of words up there. It's just a reminder. So when you go back to study, you're like, why did Jen do it like this? Because it says at least 5 trucks. So why didn't she go up? I'm going to show you what we would do with the complement instead, because it would involve writing a whole lot less. Okay. So first thing, because we have 50 trucks, that's our N in this case. And because we said that there's a 10% chance of breaking down, That's our P. That's our probability of a success. So I'm going to write P up here. Okay. So we can either use Q or we can use 1 minus P for your probability of a failure. I'm going to write Q right next to it. Q is always equal to 1 minus P. So what would 1 minus P be for this one? Perfect, 0.9. Okay, so probability of a success is 0.1. Probability of failure is going to be the complement of that 1 minus 0.1, which would be 0.9. Okay, the N in this case is 50 because there were 50 trucks. So what I want to do, if I want to calculate the probability that at least 5 trucks will break down, we can write that as the probability that X is greater than or equal to 5. Okay. But again, if I were going to solve that directly, I got to do the probability that X is actually equal to 5, it's equal to 6, it's equal to 7, it's equal to 8, all the way up to 50. I don't want to do that. So I'm going to do the complement of that. So I'm going to do 1 minus the probability that X is less than 5. So I'm going to write that as my next step. So what I did is I wrote the opposite of that sign there. The opposite of greater than or equal to 5 is just less than 5. So what that means is if I can do this calculation, 1 minus, and I'm going to put this in brackets, less than 5 would mean I'm calculating the probability that X is equal to 4. Whoops, I wrote that funny. Sorry. I didn't mean to end the parentheses. Let's get rid of that part. Okay. The probability that X is equal to 4 plus the probability that X is equal to 3 plus the probability that X is equal to 2 plus the probability that X is equal to 1. And I actually have to fit one more in there. I'm already falling off the page. Plus the probability that X is equal to 0, because that's also a possibility of what could happen there. Okay. In terms of what that's going to look like using the binomial distribution stuff, what I'm going to write is 1 minus, and then the probability that X is equal to 4, the way you would do that calculation, we would take the N, which is 50, and we would put 4 below it. This says 50, choose 4. And then we put down the probability of a success. Probability of a success was the p-value, and we said the p-value was 0.1. Okay. Probability of success, we always raise that to the power of what was in the bottom that we wrote here. So I put a 4 after it. Then we put the probability of a failure, so that's 0.9. And we raise that to the power of this number minus this number. So 50 minus 4 is the power on that one. That's going to be the answer to this thing right here, if we went through and we did the whole calculation. And then we would do it again, and we're going to do it for X is equal to 3. So you would write 50, choose 3. And then you do 0.1 raised to the power of 3 this time. And then you do 0.9 raised to the power of 50 minus 3. And that would give you the answer to that one. And then we would do 50, choose 2. And you would do 0.1 raised to the power of 2. And you do 0.9 raised to the power of 50 minus 2. And then we would do 50, choose 1. 0.1 raised to the power of 1. and 0.9 raised to the power of 50 minus 1. And then we'll see if I can fit that last one there. 50, choose 0. And we do 0.1 raised to the 0th power and 0.9 raised to the 50 minus 0 power, which is just 50. I managed to just barely squeeze it in before I fell off the page. So the answer to this is 1 minus the complement of that thing. So here's the 1 minus, and then this whole thing is the calculation of the complement of that thing. That would still be a lot of things for you to calculate, but only having to do 1, 2, 3, 4, 5 of those is much better than having to do 5 all the way up to 50. Is she actually going to have you do that many of them on a test? Probably not. She'd probably just have you write this out. So when they say write the probability density function for the thing, they mean you're writing out those things. You don't necessarily need to calculate them unless she gives you a separate table. And she has to give you a very specific table for each of them in order for you to be able to use the table to do it. Otherwise, we use all the factorial stuff. Did she go through the calculations of the factorial stuff? Last quarter, they said no. I showed people how to do it, but I'll show you on the next examples. It's much easier. I'll actually show you how to do the calculation with the factorial in case you want to do it. But normally she gives you guys a table. Yes.
I'm just a little confused on like the 0.1 and the 0.9. I understand that the 0.1 came from like the problem.
Yeah.
I think there's only about the 0.
So whenever they give you the P, you get the Q for free, which is the probability of failure. This one's the probability of success. The probability of a failure is always 1 minus whatever that one is. So 1 minus this is where that one came from. So you won't see it in the problem, but you'll get it by doing 1 minus whatever the P is. Good question. Yeah. Other questions on this setup? I'm going to do another one just like it. Okay. So this would be another one where I have a whole bunch of words, and there's a whole bunch of words so that when you go back and study later, you can see what Jen did. You don't necessarily have all those words if it was just like a test question. All right, it says, a factory produces bolts. So kind of like screws, but they don't have the pointy end on them, just bolts. With a defect rate of 2%. What is the probability that a sample of 100 bolts will contain at least 3 defective bolts? Okay. So it says at least 3 defective bolts. So at least 3 would mean we could have 3 or 4 or 5 or 6 or 7 up to 100. You don't want to have to add all those up to 100. That would be terrible. So instead, you would want to do the opposite of at least 3. You'll do 1 minus the complement of that. And so then you would have or actually less than 3 will be the direction that we're going to go. So what I have in words here is the number of defective bolts in the sample follows a binomial distribution, because if they're either going to fail or not fail, or be defective or not be defective, that's what makes it binomial. There's only 2 things it could be. And so the probability that a sample contains 3 or more defective bolts is the cumulative probability of 3 defective bolts plus 4 defective bolts plus 5 defective bolts all the way up to 100 defective bolts. You don't want to do that. Instead, it's easier to compute the complement. So for us, if I want the probability that X is at least 3, that's the same thing as 1 minus the complement of that. And you're just going to turn that sign around and not put the little line underneath it. That's the probability that you have fewer than 3 defective bolts. Easier calculation for us. Okay. What's our P in this problem? Beautiful. So our P, that 2%, is 0.02. So what's our Q? 0.98. Let me explain that. If the defect rate is 2%, then there's a 98% rate that they're okay, right? And 98% is going to be 0.98. Again, it's going to be 1 minus whatever that is. 1 minus 0.02 is 0.98. Well, actually, defective bolts is 2%. Good bolts is 98%.
Of ridiculous quantities.
Mhm.
2% of them are all bad. That's a lot.
Yeah, 2% of them out of 100. What's 2% of 100?
At least 200.
So you have 100 bolts sitting there. On average, 2 of them should be bad, but 98 of them should be good. Okay, so that's using averages, but what this is asking us is for probabilities of certain scenarios. And in this case, they want to know what's the probability that in 100 bolts, we've got at least 3 that are bad. On average, 2 should be bad, right? So what's the probability that 3 or more are bad is what they're asking. Okay, so we're again doing the same probability density function idea that we were doing before. And you're going to use that your n is 100. You're going to use that your p is the 0.02 and the q is the 0.98. So to do this one right here, this is the same thing as 1 minus the probability that x is equal to 2 plus the probability that x is equal to 1 plus the probability that x is equal to 0. Because if x is less than 3, that means it could be 2, or it could be 1, or it could be 0. But we can't have negative bolts, so we got to stop at 0. So if she asked you to write the probability density function for this, you would say it's 1 minus, and then we're going to do, there were 100 bolts, choose 2 of them. Now we write the probability of a success. We said that 0.02, and we raise it to the power of that bottom number. And then we do the probability of a failure, that's 0.98, and we raise it to the power of 100 minus 2. That would give us the answer to this one. And then we'll do 100, choose 1. And you'll do probability of a success, 0.02, raised to the power of that bottom number 1, times the probability of a failure, 0.98, raised to the power of 100 minus 1. And that will give you the answer to that part. And then we'll do 0. 100, choose 0. And we'll multiply by the probability of success raised to the power of that 0. And then the probability of a failure raised to the power of 100 minus 0. And so if you did that calculation, that's going to give you the answer. You'd probably leave it right there, unless she gave you a table. But I'll do the actual calculations for the ones on the next page so you can see what that looks like when we get numbers. Okay. A survey at UC Davis had 2 response choices, either yes or no. So this makes it binomial. All undergraduates were given the survey and 82% of them responded yes. So our probability of a success is 0.82 for this one. What would be our probability of a failure? Perfect. So 0.18 would be your probability of a failure. You're just going to do 1 minus the probability of a success. Suppose you pick 9 random undergraduates from the survey. You are interested in the number who responded yes. So what does the random variable x represent? The random variable x represents the number of students out of the 9 that you selected who said yes. The next part, it has x with the little squiggle after it. What this is asking is, how do you write this distribution? And so when she does that cute little squiggle like that, after the squiggle, you're going to either put binomial, uniform, or normal at this point, because those are the only things you've learned. Because this is a binomial distribution, we're going to write binomial after the squiggle. And then we put an open set of parentheses. And on the inside of the open set of parentheses, the first thing you always put is the n, and then you put a comma, and then you put the p after that. So for this one, our binomial distribution has an n of 9, and the p was 0.82. And that's what we would just write if she said describe this distribution. You'd write it was a binomial distribution. The first thing you'd write is the n value, and then after the comma, you'd write the p value. We don't write the q value in there because we could figure that part out. So she doesn't need that part.
The 9 is the 9 students, right?
Yes, yes. So if it said, suppose you pick 11 students, you would make your n 11 instead. All right. Question C says, what values does the random variable x take on? So the biggest value that it could be is 9. If you ask the 9 students and all 9 of them said yes, that's the biggest value it could be. What's the smallest value it could be? 0, because 0 of them could say yes, right? So when it says what values does the random variable x take on, x takes on the values from 0 to 9. And it says, give the binomial PDF for this situation. That's the probability density function. That's the crazy formula thing we've been writing. So you're going to give just the general formula here that the probability that capital X is equal to a lowercase x is equal to n choose lowercase x times p raised to the power of that lowercase x times q raised to the power of n minus x. That's the general probability density function. We can do better than that for this particular probability density function. So we're going to write for this one, the probability that x is equal to x is, instead of n, I'm going to write what n is actually equal to. We have 9 for this problem. We're going to leave it a lowercase x because we can change that and use it for each of the individual things they could ask us. If they ask us if 1 student does it or 2 students does it or no students do it, we can change that little x at the bottom. The p isn't going to change though. It's going to be 0.82. And we're always going to raise it to the power of whatever that x is. And then the q isn't going to change. It's going to be 0.18. And we're always going to raise it to the power of n, or sorry, not n, 9 minus x for this one. So this would be our probability density function for this particular problem. This is the general probability density function for any binomial distribution. How you doing? Dying, Jen. We're dying. Question?
So we're only keeping that X because we can just plug in whatever.
Because you could plug in 0 all the way through 9. Yep, perfect. All right. Here's your first test question. On average, how many of the 9 students would you expect to answer yes? Okay. When I ask for an average, we talked about how average could be so very many things in statistics, but for this particular problem, the average is referring to the mean. There's a formula for calculating the mean when it's a binomial distribution. Anybody have that in their notes? What's the formula for the mean for a binomial distribution? You remember? It's going to start with a mu and it equals, it's going to have an n in there. Times p. Whenever it's a binomial distribution, the mean is going to be n times whatever p is. Not too hard to remember because n and p are like the crazy important parts of a binomial distribution because we always put the n first and the p second. So that's my n and that's my p. You got to multiply them together. That's going to give us our average every time. So we're going to write that our n is 9 and our p is 0.82. And we're going to figure out what that is. 9 times 0.82. Comes out to be 7.38. So on average, we expect 7.38 students out of 9 are going to say yes. Does that mean that's going to happen every time? No, but on average, that's what should happen when we ask 9 students if we have a probability that 82% of them should say yes. Okay. Then it says, what is the standard deviation? This one is also a formula that she'll give you. The standard deviation for a binomial distribution is the square root of n times p times q. And she could write q or she could write 1 minus p because remember q is always 1 minus whatever the p value is. So for us, it's the square root of 9 times 0.82 times, and you guys told me that my q is 0.18. So that should be did you get 1.153 approximately? So most likely those will be things that are on a formula sheet, but what you'll have to be careful of is right now we're talking very specifically about binomial distributions. she'll have problems on the midterm where it actually won't come from a binomial distribution. So if you use those formulas for the mean and the standard deviation, you'll get it wrong. So you have to pay attention to what kind of distribution you're working with when you're looking at her formula sheet. So the formula sheet's great, but what I find is the biggest challenge for students in statistics is they'll come in with that formula sheet and then they just start using it. And then I go, oh shoot, you just calculated the mean for a uniform distribution, but you wanted it for a binomial distribution. They're like, oh, it's different. I'm like, yes, it matters what kind of distribution we're talking about. So this is only the formula for the average or the mean for a binomial distribution. And this is only the formula for standard deviation for a binomial distribution. We have to be careful. All right. Now, an actual calculation. What is the probability at most 7 of the students responded yes? Okay, so at most means 7 could, but 6 could, or 5 could, or 4 could, or 3 could, or 2 could, or 1 could, or 0 could. So I have 8 things that I would be calculating if I go that direction. But the biggest value n could be is what? Yeah, in this case, the biggest value that our n could be, we said it was 9. So instead of me doing 0 all the way up to 7, it would be better for me to do the complement, in which case I only have to do 8 and 9. Way faster. So I'm going to do the complement, but I'll write it out so that you can see what this looks like. So if I want the probability that x is less than or equal to 7, it's going to be easier for me to do 1 minus the complement, which is the probability that x is actually greater than 7. Then I only have to do 2 of those crazy binomial things. It's going to be 1 minus the probability that x is equal to 8 plus the probability that x is equal to 9. So that'll be 1 minus. And then if I want to do the probability that x is equal to 8, we do n choose 8. In our case, n is 9, so 9 choose 8 times the probability of a success. We said our p was 0.82, and we're going to raise it to the power of that 8 down there. Times the probability of a failure, we said was 0.18, and we're going to raise it to the power of that 9 minus that 8. 9 minus 8 is just 1 here. That's one calculation we're going to do. And then we're going to do the calculation for x is equal to 9. So that's going to be 9 choose 9 times the probability of a success, which is 0.82. We always raise it to the power of the bottom number there. So that's a 9. And then 0.18 raised to the power of 9 minus 9, which is going to make it to the 0th power. I was having us leave these for the last problem because there were a bunch of them to do. There's only 2 of them to do. So I'm going to do these ones so you can see how I would do the calculation. This 9 choose 8. That's a factorial thing. 9 choose 8. I write 9 factorial over 8 factorial times 9 minus 8 in parentheses with the factorial after it. Yep. 9 factorial over 8 factorial times 1 factorial is what that simplifies to. Okay. And then remember, 9 factorial just means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 1 factorial just means 1 because it doesn't have anything lower than it for me to go with. So 1 factorial is always 1. And 0 factorial is always 1 as well. That's just a definition. That one's weird. 0 factorial, you just have to memorize, is 1. Okay, so 9 factorial divided by 8 factorial, and this is just a 1, so you can ignore that one. That's got to just be 9. Because 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, if you do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 underneath it, everything with the 8s and the 7s and the 6s on down are going to cancel. The only thing that's not going to cancel is the 9 in the top. So this comes out to be the number 9 when you do that calculation. 9 factorial divided by 9 factorial. Well, I have to write this out. I'll show it to you. This is 9, choose 9. That's 9 factorial in the top over 9 factorial in the bottom times 9 minus 9 inside parentheses with the factorial on the outside. That's 9 factorial over 9 factorial times 0 factorial. But I said 0 factorial, we just memorized, that's 1. So 0 factorial disappears. You have 9 factorial divided by 9 factorial. Just 1. So here's a hint. Anytime you've got combinations where it's exactly the same number over exactly the same number, it always comes out to be 1. So if this said 10 choose 10, it would also be 1. If it said 100 choose 100, it would also be 1. It always comes out to be 1 if they're the same number. So you don't even have to do the calculation. Okay. I just did those so that I can substitute them back into the formula up here. So I have 1 minus, and then instead of writing this 9 choose 8, we just figured out 9 choose 8 is just the number 9. So you have 9 times 0.82 to the 8th power. Obviously, that's a calculator problem. We're not going to do that in our heads. Times 0.18 to the 1st power. Plus, and then we just figured out 9 choose 9 is just the number 1. So this would be 1 times 0.82 to the 9th power. Again, definitely a calculator problem. We're not going to do that. And then 0.18 to the 0th power? What's anything to the 0th power? It's actually 1. So anything to the 0th power just becomes the number 1. And now we'd pop that into a calculator. So this is going to come out to be 1 minus this first number here. When you pop it into the calculator, it comes out to be about 0.33 if we round it. And this second number here comes out to be 0.17 if we round it. So we have 1 minus, if you combine those together, that's 0.5. 1 minus 0.5 is 0.5. So what does that say? That says the probability that at most 7 of the students out of the 9 responded yes is about 50%. So that 0.5 is 50% as a probability. Exactly the same idea to answer the bottom one. What is the probability that at least 2 students responded yes? Probability that X is at least 2 is written like that. But I would have to do 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 if I do it that direction. If I don't want to do that many, I could do the complement, which would be 1 minus the probability that X is less than 2. So then this is going to be 1 minus the probability that X is equal to 1, because that would be the first thing less than 2, plus the probability that X is equal to 0. And so we only have to do those 2 calculations instead. Much easier. So we would do 1 minus, to do the probability that x is exactly equal to 1 would be 9, choose 1, times the probability of a success is 0.82. We raise that to that bottom number 1, times the probability of a failure, 0.18, and we raise that to the power of 9 minus 1. And that would give us that one. And then probability that x is equal to 0, that would be 9, choose 0. We multiply that by 0.82 raised to the power of that bottom number 0. And 0.18 raised to the power of 9 minus 0, so that would be to the 9th power. So again, I got to go figure out what's 9, choose 1. That's going to be 9 factorial over 1 factorial times 9 minus 1 in parentheses with the factorial on the outside. So that's 9 factorial over 1 factorial times 8 factorial. But you actually already did this calculation. It's backwards from what we did up here, but we have a 9 factorial in the top. We have the 1 factorial over here for this one, and we have the 8 factorial in the front for this one, but it's the same calculation. That one also comes out to be 9. And then 9, choose 0. That's going to be 9 factorial over 0 factorial, which remember is just 1. And then times 9 minus 0, parentheses, with the factorial on the outside. That means that this is 9 factorial over 9 factorial. So that's also just 1. So 1 minus, instead of writing 9, choose 1, I'm going to write 9 times 0.82 raised to the first power times 0.18 raised to the 8th power. And then I'm gonna substitute in 1 for that 9, choose 0. Times 0.82 to the 0th power. Anything to the 0th power is just 1, so that's also a 1 right there. Times 0.18 to the 9th power. Okay. Okay, so this number's wild. It's 1 minus, and then this part comes out to be 0.0000081 plus, and then this one comes out to be 0.18 to the 9th power is 0.00000002. If I put those together, that's essentially 0. I could have a really tiny number out here, but it's basically going to be 1 minus 0 if I'm rounding to like 2 or 3 decimal places. So if it comes out to be 1 or essentially 1, what does that mean in terms of a probability? Yeah, 100%, because when we said 0.5, that was 50%. If it's 1, it's essentially 100%. So it's not exactly 100% because these weren't exactly 0, but they're pretty close to 0. So you would say the answer is practically 100%. So I'm going to write that in words. Practically 100%. Question?
So is the formula the same if you solve using the opposite of formulas or something? This one maybe we still.
So if you did this instead, so you did the probability that x was equal to 2 plus the probability x is equal to 3 plus the probability that x is equal to 4 all the way up to 9, you'll get exactly the same answer as doing this. But instead of you having to do a bunch of those, we only have to do 2 when we do the composite.
So it's just the exact same formula. And then we get the
Yes.
Same thing.
You'll get exactly the same thing, but what we're trying to do is cheat and do less work, because otherwise it's just so many calculations. So when I've seen her ask people to write stuff out, usually it's something that involves the complement like that, so that like if you did it the other way, you'd be writing out an insane number of things, but if you use the complement, you're like, oh, there's only 2 things to write, it's not that big of a deal. So that's why I try and do a bunch that are like that, so that you're not like,
But you don't change anything, right?
nope. So this was all binomial distribution stuff, and I know that was a few days ago. Then you guys moved over into uniform distribution. Okay. These distributions are all like, they come up in different sort of situations. And so you have to be able to like read the problem and identify what kind of distribution it is, because often the problem doesn't tell you this is a binomial distribution. So like this problem, nowhere in the problem did it say that you're going to write the binomial distribution formula or any of that out there. The only thing that let me know it was binomial was that the survey had 2 choices, yes or no. And I went, oh, binomial. Uniform distribution ones actually frequently will have the words uniformly distributed in there, or they'll say there's an equal likelihood of any of the probabilities happening. So if it doesn't say uniformly distributed, but it does say something like every single possible value of X has the same probability, then it's a uniform distribution. So uniform means it's the same for all of them. So this first one says the age of cars in a parking lot at a community college is uniformly distributed from 6 months to 9.5 years. So what that means is I walk out to the parking lot and the first car I look at is equally likely to be 6 months old or 9.5 years old. Equally likely. So it's not like this is a parking lot full of old cars, or that it's a parking lot full of new cars. It's equally likely that it could be 6 months. It could be 9 years old. It could be 9.5 years old. Equally likely any of those ages. Okay. Is that like realistic in the real world? No. But we're going to go with it. What is the average age of all the cars in the lot? The word average again is the mean. This is asking us for the mu, and if you weren't paying attention, you might look on your formula sheet and go use the n times the p that we did on the last thing, but that doesn't make any sense in this problem. N and p are not things that come up in a uniform distribution problem, so we have to be like, oh, okay. So I have to know this is a uniform distribution problem to know how to answer this next question. So first thing I gotta know, when we're doing a uniform distribution, it matters what the smallest value is and what the biggest value is. And I want to make sure my units are the same, because if I said my smallest value here is 6 and my biggest value here is 9.5, I'm going to be wrong. Why am I going to be wrong? If I said the smallest value was 6 and the biggest value was 9.5, why am I lying to you? One's in months and one's in years. So instead of saying 6 months, what could I say instead? Half a year. Perfect. Now we're in the same unit. So I want to be careful of that with these types of problems. I'm going to change this 6 months into 0.5 years. And then what I have is a thing that is uniformly distributed. All right, so with my uniform distribution, there's a formula that says this. The mean is A plus B divided by 2. That's only helpful if we know what A and B mean. Whenever we do A uniform distribution problem, the A is always the smallest value and the B is always the biggest value. So in this problem, my A is 0.5 years and my B is 9.5 years. And now I can go ahead and go find that average. So this is going to be 0.5 plus 9.5 divided by 2. And we can totally do this one without a calculator, because that's 10 divided by 2. Which is 5 years. So the average age of all the cars in the lot is 5 years. When she drew you pictures of uniformly distributed things, she drew you rectangles. So once you got to normal distribution, that was when you had like your bell-shaped curve that we're familiar with. But anytime we're talking about uniform distribution problems, because the likelihood is equal for uniform distribution, it doesn't do the cool curve. It's literally a rectangle. The height stays the same for all of them. So I'm going to draw a picture to answer the next part of the question. What is the probability that a randomly selected car is less than 4 years old? Okay, I need a picture. So what I'm going to draw is a rectangle where my starting value down here at the bottom is 0.5. And my ending value over here at the other end is 9.5. So the rectangle is going to look like this. And if I found the area of this red rectangle here, then I would know the probability. Now, the probability all the way across the rectangle, if I filled in the entire rectangle, should be 100%. When you fill in the whole rectangle, it should always be 100%. Okay? If I want to find the area of a rectangle, I need two things. This is just from geometry, not statistics. Do you remember what I need to find the area of a rectangle? The base times the height. The base is going to be easy because it's the distance from 0.5 to 9.5. What's the distance from 0.5 to 9.5? 9. So our base is 9. The height is a little more complicated, but not too much so. This involves the probability density function for a uniform distribution. So here's the probability density function. F of x is always equal to 1 divided by b minus a when we're talking about uniform distribution. So this is the probability density function. We call it a PDF. And what it always represents is the height of the rectangle. So anytime we're doing a uniform distribution problem and you got to go figure out the height of the rectangle, you're going to do 1 divided by the biggest number minus the smallest number. And in this case, our biggest number was 9.5 and our smallest number was 0.5. So for us, this is going to be 1 over 9.5 minus 0.5, which is just 1/9. So the height of our rectangle is 1/9. So I'm going to go ahead and write that over here off to the side, that our height is 1/9. And then you guys told me that my base all the way across was 9.5 minus 0.5. That came out to be 9. And I said, if we did the entire rectangle, it should always multiply to give us 1. 9 times 1/9 gives us 1. So you did this right. Nicely done. But that's not the answer to this question. But this is always the setup. It's always how we get started. We got to figure out the base and we got to figure out the height. Then we answer the specific question. The specific question says, Find the probability that a randomly selected car is less than 4 years old. Okay. These are the ages along the bottom, 0.5 years all the way to 9.5 years. So if I want less than 4 years old, then I'm not going all the way across and doing the whole rectangle. I'm just going to do part of the rectangle. And that part of the rectangle, let's see. I need a color that's going to show it better. How about purple? Okay. So if this is 0.5 and this is 9.5, 4 is maybe like right here. I'm just going to draw a line and call that 4. There's my 4. Okay. I want just that part of the rectangle because it says less than 4. If it said bigger than 4, I'd want to shade this side of the rectangle. But it said less than 4, so here's my 4 and I'm doing everything less than it. And so literally I just want you to find me the area of this rectangle. Not the whole rectangle, the area of the little rectangle. So I went out to 4, but the first number is 0.5, so how long is the base? 3.5. But what's the height? It stayed 1/9. So the height didn't change on the rectangle, we're just changing the base. So the answer to this question, that it's less than 4 years old, so the probability that x is less than 4 is equal to your base times your height. And you said the base was 4 minus 0.5, and our height is 1/9. So 4 minus 0.5 you said was 3.5. That's going to go in the numerator. And 9 goes down in the denominator. So 3.5 over 9. If you have a calculator, you could get like a decimal approximation of that. If you don't, 3.5 over 9 is fine. The decimal comes out to be 0.3888888 forever. So I'm going to say 0.39. So what does that mean in terms of the car? If I walk out to the parking lot, the probability that the car that I just like randomly look at is less than 4 years old is 39%. Considering only cars that are less than 7.5 years old, find the probability that a randomly chosen car is less than 4 years old. This is that given idea that we talked about before. If I want to only consider cars that are 7.5 years old or less, then what I'm writing is given that x is less than 7.5, find the probability that the randomly selected car is less than 4 years old. The number before the given bar is x is less than 4. So the probability given x is less than 7.5, that x is less than 4, is going to involve us making a fraction with 2 areas. The area in the top is going to be the probability that x is less than 4. We just did that. That was this number right here. In the bottom, we need the probability that x is less than 7.5. We're going to do another rectangle. All the way across again ends at 9.5 if we did the whole rectangle. The height of that rectangle is still 1/9. Nothing changed about that. But we're only going to go out to 7.5. and find this area. So your base is 7.5 minus 0.5, so it's 7. And your height is 1/9. So this is the denominator. Base times height is equal to 7.5 minus 0.5 times the height, which is 1/9. 7.5 minus 0.5 is 7 times 1/9 is 7/9. I'm calling that the denominator because that was this part. It comes after the given bar. That's the denominator. The numerator is this, but you already did that calculation right here. So we're going to use the 3.5 over 9 for the numerator. We're going to use the 7 over 9 for the denominator. Okay, so if we've got a numerator of 3.5 over 9, so this is my probability that x is less than 4, given that x is less than 7.5. The numerator is 3.5 over 9 divided by, the denominator is 7 over 9. Do you remember how to divide fractions? Keep the top fraction. Change that division bar in the middle into a multiplication dot, and then flip over that bottom fraction. So instead of 7/9, you're going to write 9/7. And then what that allows you to do is cross cancel those 9s out. That 9 and that 9 are gone. So you have 3.5 over 7. Do you happen to recognize that 3.5 over 7 is easy to simplify? What's that come out to be? 1/2. 3.5 is half of 7. So this actually comes out to be 1/2, or 0.5 if you want to turn it into a decimal, because we've been using decimals for these. So considering only cars that are less than 7.5 years old, the probability that a randomly selected car from that group is less than 4 years old is 50%. That's what we just figured out. The last part. Find the third quartile. Oh, question?
Yeah, she did something like this in class yesterday, but she did it like differently, where we like found the intersection instead. It was like the question was basically asking, maybe it's just formatted differently. So it was like we have to find the intersection instead of that.
So the thing about these problems is that if you choose to do them with the geometry, they're heck easy. If you decide to draw out the rectangles and then shade in stuff, you often get to skip over having to do the intersections and whatever. It's not that they're wrong, it's just a different way of doing it. So if this way makes more sense, cool. If her way makes more sense, also totally fine. But yeah, you're always allowed to just draw rectangles when it's uniform distribution problems. And since I really think rectangles are pretty easy, I tend to stick with trying for rectangles, because there's just, if you understand this, you'll get them right all the time. And you're not memorizing any formulas. You're just like, I can find the area of a rectangle. Yay. The last one goes back to that percentile idea that we had talked about before. If we're talking about the third quartile, that's the same thing as the 75th percentile, right? So when she's saying find the third quartile of ages of cars in the lot, that's the same thing as saying you want to find a value such that 75% of cars are at most or less than or equal to that particular age. So if you want the 75th percentile, here's our formula. She's going to give it to you on a formula sheet, so it would be a thing you're going to have. You do the 75 over 100 part. That seems probably familiar. Then we do B minus A. So I should probably, before I put the 75 over 100, I'm going to put the percentile K over 100, and then I'll fill in the numbers in just a second. Plus the smaller number A. This is the formula we're going to use. So for this one, the K is 75. The B is the bigger number. Our bigger number was 9.5. Minus the smaller number. Our smaller number was 0.5. And then we always add it to the smaller number, which is 0.5. So that'll be on the formula sheet. 75 over 100 is the same thing as 3/4. 9.5 minus 0.5 is just 9. So this is going to be 9 times 3/4 plus, and if you want, you can turn 0.5 back into 1/2 if you want it to all be the same, or you can keep 0.5. It's up to you. So this is going to be 27 over 4 plus 1/2 is the same thing as 2/4. So I got 29 over 4, which 29 over 4 is 7.25. So I'm going to write years after it because this is talking about an age. It says find the third quartile of ages of cars in the lot. So if you found a car that's 7.25 years old in the lot, 75% of the cars are younger than it, and 25% of the cars are older than it. Okay. Question.
Uh, let's see, you talk again how you got the P, probability of X, less than 4, given X, the top part.
So considering only cars that are less than 7.5 years old, so that's why this part was the denominator part of our fraction. So we went ahead and we made the rectangle stop at 7.5 for the bottom. Find the probability that a randomly chosen car is less than 4 years old. So that's this part. That means it's going to be in the numerator because it's coming before that bar there. We already did that calculation up here in part B. And we got 3.5 over 9 for that. So that's why I didn't do that calculation a separate time. We had already done it. So this part goes in the numerator. We calculated it up here and it was 3.5 over 9. This part goes in the denominator and we calculated it right here. That was 7 over 9. So I took the 3.5 over 9 and I put it in the top, and the 7 over 9 and I put it in the bottom.
I see, okay.
Is that okay?
Yeah, thank
Yeah, I kind of skipped a step because I borrowed the number from part B. So the next page is all uniform distribution stuff again. It says a random number generator picks numbers from 0 to 9 in a uniform manner. So they told us it's uniform. If we want to do the little distribution thing again, once you see the little squiggle, the only things we're going to write are either binomial, uniform, or normal, because those are the only things we've learned so far. We're going to write uniform. And then after that, inside the parentheses, you always put the A, comma, the B. The A is always the smaller value, the B is always the bigger value. So when I go to write it for this particular one, we have X squiggle, uniform. Our A, the smaller number is 0. And our B, the bigger number is 9. How do I say this properly? We don't say squiggle, I just wrote squiggle. But it says X follows a X follows a uniform distribution from 0 to 9. All right, when it says graph the probability distribution, anytime it's a uniform distribution, it's going to be a rectangle. The smallest value on this rectangle is a 0. The biggest value on this rectangle is a 9. If I asked you for the base of this rectangle, you're going to say 9, but we need the height. When it says, what's the formula for the PDF? That's always 1 over B minus A. And that, again, is always going to be the height of the rectangle. So we have 1 over, our B is 9. Our A is 0. So our height, again, is 1/9 for this rectangle. It doesn't always come out to be 1/9. That's a coincidence. What is the mean and the standard deviation? Okay, the mean is always A plus B divided by 2. In this case, that's 0 plus 9 divided by 2, which is 9 divided by 2, which comes out to be 4.5. Okay, the formula for the standard deviation, she's going to have to give you, it's a weird one. It's the square root of B minus A in parentheses squared divided by 12. And she could do a whole explanation of where that 12 came from, but for the most part, people don't really care. It's just a formula that will be on a formula sheet. So for us, our B is 9, our A is 0, which means we have the square root of 81 over 12, which comes out to be approximately 2.6. All right, when it asks you to find the probability and then it doesn't even have words anymore, this is saying find the probability that X is greater than 4.2, but it's smaller than 8.5. I'm always going to draw a picture. There's other ways to do it. She might give you formulas and stuff, but you can always draw the rectangle, and I think that's the easiest way to tackle it. So I'm going to draw the same rectangle I already drew. My rectangle starts at 0, goes all the way to 9, and it has a height of 1/9. I'm going to start with the same rectangle. Okay, but now it specifically says X needs to be bigger than 4.2. So along the bottom here, if that's 0 and that's 9, I'm going to put 4.2 like right there. But X is smaller than 8.5, so I'm going to put 8.5 like right here. If it's bigger than 4.2 but smaller than 8.5, they're talking about this rectangle right here. And so you don't need any crazy formulas. You just have to be able to tell me what's the area of that purple rectangle that's inside there. What's the height of the purple rectangle? Yeah, that part doesn't change. The only thing that's changing is the base, because now we're not going from 0 to 9. We're just going from 4.2 up to 8.5. So to find that base, you're going to do 8.5 minus 4.2, and you're going to multiply whatever you get by 1/9, and that's it. Way easier to do it this way. You could use her formulas, but you're always allowed to just do this. Height is always going to come from this formula up here. It's always going to be 1 over b minus a. So I'll write that off to the side. This is always the height. So for uniform distribution problems, always that's going to be the formula. It's the same thing as her asking you for the PDF. The probability density function is the height of our distribution. So our calculation, I need the base times the height. The base is 8.5 minus 4.2, and the height is 1/9. So 8.5 minus 4.2 is 4.3 over 9, which, if we have a calculator, comes out to be approximately 0.48 if we round it. So the next one says, find the probability given x is greater than 3 that x is greater than 6. Okay, so we again have a numerator and a denominator situation. So we got to find two rectangles for ourselves. We're going to find the area of that rectangle. That's going to go in the top. We're going to find the area of that rectangle. That one's going to go in the bottom. I'm going to run out of time on that. So if you have to go, that's okay. But I'll finish it here and then I'll upload the video. So if you have to go, that's okay. All right. So probability that, we'll do my numerator calculation first, that x is greater than 6. My base then, let's draw a picture. So I'm going to say 6 is like right about here. X is greater than 6 is just going to be shaded this way because greater than, I want to go towards the 9. If it said less than 6, we'd go the other way. Okay. So my base is just going to be from 6 to 9. So base is going to be 9 minus 6 times my height. The height on these rectangles is going to stay 1/9. So 9 minus 6 is just 3. And then 1/9 is, when I multiply the 3 times the 1/9, I get 3/9, which you could simplify to 1/3 if you want. That's my numerator. For the denominator, we're doing x is greater than 3. Okay, so if x is greater than 3, let's say 3 is right here then. So x is greater than 3 is going to be this whole rectangle here. So now my base goes from 3 to 9. So 9 minus 3 times, and then the height doesn't change, it stays 1/9. So that comes out to be 6/9, or 2/3. Okay, so my numerator is 1/3. And my denominator is 2/3. So I'm doing 1/3 divided by 2/3. So we keep the top fraction, we change that big division bar in the middle and do a multiplication dot, and then you're going to flip over that second fraction. So it's going to be 3/2 now. And so you can cancel out the 3's this way. So we end up with 1/2. Or 0.5 if you want to turn it into a decimal. If you look at the picture, that kind of makes sense. If that is the area for the x is greater than 6, and that's the area for x is greater than 3, the picture actually looks like it's half of it, right? So you can totally use the formulas to figure them out, but I honestly think drawing the rectangles ends up being less complicated if you understand how the rectangles work. All right, good work today, guys. If you didn't get a chance to sign the sign-in sheet, it's over there on the table on the way out. Thank you.